So, students, after discussing about superposition principle, let's talk about standing waves and normal modes. Okay. So, standing wave, as you can see it from the word which is written here, that it should not show any type of movement. So, here we are talking about the string, and the string is stretched along its length, and the two ends of the strings are fixed to the wall, and such type of the wall is what? It does not absorb any type of the energy. The condition is that. Okay. So, this type of the arrangement is there. This is the string and this is the wall which is not allowing any energy to transfer. Okay. If I generate any disturbance in the spring, so it will be carried. If I generate it from this point, it will be carried towards this point. So when it strikes this point, it may not transfer any type of the energy to the wall. Okay, because due to the property of that wall. So what will happen when it will be created like this? It will be what? It will be reflecting the same amount. Okay, it will be reflecting the wave somewhat like this in the opposite direction. And what will be the nature of that wave? Okay, the nature of that wave will be as such that the amplitude will not change because there is no loss of energy in that case. Okay, it is completely reflected. So here you can see that I am having two waves. Okay, one is moving in the positive x direction that I have shown by y1, and one wave is reflected wave that is shown by the parameter y2. Okay, and we know that it is a sinusoidal wave. Two waves are sinusoidal wave. One is what? Incident wave, and the other is reflective wave. Incident and the reflected wave. Okay, so in this case, what happened? In this case, if the wall is rigid, okay, the wall is rigid, so what happens? Reflection takes place. At the same time, what happens if any ray incident on that wall, then it transmits its energy. But if the wall is as such that it does not allow any absorption of energy, so it will be reflecting that much of amount of energy in the opposite direction. Okay, and that what it is happening here. So here you can see that two displacement equations are written. So what will happen? They will superpose. Okay, they will superimpose on one another. So what will happen? We have to apply the principle of superposition, and that's what I did here. Okay, so this is the displacement of the resultant wave which get formed. Okay, we have studied the principle of superposition. So this is the resultant wave, the displacement in case of resultant wave. So what happened? We have to add these two equations, and after adding, what I did, I applied the sin A plus sin B formula, and we know that it is equals to 2 into sin A plus B. If I consider this quantity to be A, if I consider this quantity to be B, so what happens? A plus B upon 2, and that's what we get here with sine. Okay, because the formula is sin A plus sin B is equals to 2 into sin A plus B upon 2 into cos of A minus B upon 2. Okay, this is simple mathematics. So from here you can see now in this equation the value of this propagation constant and position and this omega t is coming what separately. It is not coming like this in a single phase. Okay, it is coming separately. So here what you can see that the wave which we get, the resultant wave after superposition, is having the angular frequency omega that is same. Okay, but in this case the amplitude is not fixed. Here what I have taken, here I have taken the amplitude fixed because there is no energy transfer to the wall, and the same energy we are getting back. So but here in this case what happens? The amplitude of the resultant wave which get formed is what? Is changing. And how it is changing? It is changing with position. But what is another conclusion? The resultant wave which get formed has same angular frequency. Okay, so this is the amplitude term, that is equals to 2 into A into sine of k into x. Okay, so that means starting from here we will be getting another wave. Okay, now after some time we will be getting what? We will be getting another wave, and this is the equation of the standing wave. Okay, the process of incidence and the process of reflection goes on and on like that. Okay, in case of formation of standing wave, the process of incident and process of reflection goes on and on. So like this, if the wave is produced from here, it will be striking this and it will be again coming back and it will be striking this and again coming back like this. So to and fro it is moving like this. But after some time what will happen? A steady state will reach, and that steady state will be the state in which we will be getting the standing wave in this stress string. Okay, in this stress string we will be getting a standing wave. So let us suppose that like this type of the structure we will be getting in the string. Okay, our string will be supposed to be in this form, in this form, in this form, like this form in between two bars. So this, you can see that the oscillation is taking place. Sometimes it is vibrating in this along this loop. The string is vibrating along this loop like this, and the oscillation is as such that with increasing position you can see. If I suppose that this is x is equal to 0, with increasing position you can see that the amplitude is varying. The amplitude of the oscillation is varying, you can see like this, and it is becoming what? Less. So what we will be getting at x is equals to 0. At x is equals to 0, you can see that there is the minimum amplitude. Okay, if you put here x is equals to 0, then you will be getting sine 0, and sine 0 is what? 0 into 2a. That means at x is equal to 0, we are getting the 0 amplitude. Similarly, for x is equals to L, what you will be getting? You will be getting another amplitude, but with increasing x you can see, that with increasing position, the value of the sine will increase. Okay, the value of sine theta will increase, it will be coming close to 1. Okay, so you can see that at appropriate value, when this value will become 90 degree, okay, then you will be getting the maximum amplitude of 2a. Okay, because sine 90 is 1 in that case. So this is the rough figure which I have drawn here. Okay, but for some value of sine, you will be getting the maximum amplitude, that is 2a. Okay, and what is the minimum amplitude? That amplitude is equals to what? That will be equal to 0. Okay, so let's talk about that. What is the amplitude factor? What is the frequency factor in this case of standing wave? So the main conclusion is that the amplitude varies, and for the point at which the amplitude is 0, that point will be known as node. Okay, so at that point where the amplitude is 0, that point will be known as mode. And in this normal mode simply means what? This means the modes of the frequency. Okay, this means the modes of the frequency that varies over the entire string which is there vibrating. Okay, so here what we will be getting? We will be getting the varying amplitude, and at the point at which the amplitude is 0, that point will be known as node, and the point will be there where the amplitude will be maximum. When the value of the sine px will be equal to 1, that will be the maximum value of sine. In that case, we will be getting 2a. So, for example, if I consider this figure, this is the figure of the oscillation of the string. Okay, when the standing waves are generated. So you can see that the amplitude are minimum at these 2 points. At x is equals to 0 and at x is equals to L, that is the total length of the string. Okay, so but the amplitude is maximum where? In the middle you can see, it is maximum. So here it is denoted by A. This is known as the antinode, where the amplitude is what? Where the amplitude is maximum, and these points are known as the point of nodes. These points are known as the points of nodes. So here in this entire string, since you can see that the length of the string is fixed, so the frequency or the wavelength of the oscillation will also not go to what? Infinite. It cannot go to infinite. This wave cannot travel to infinite. Okay, this is fixed. So that means we are having some fixed values of the frequencies. Okay, we are having the fixed value of the frequency as it is written in the book also in the NCERT. The system cannot oscillate with any arbitrary frequency. Okay, but it's characterized by a set of natural frequencies. Okay, it will be having some fixed frequency with it, and such frequency will be considered to be the modes of the oscillation, and that's why I have written here this normal mode. This normal mode stands for the modes or the frequency that the system will have during its oscillation. Okay, so here you can see, let's talk about this factor, the amplitude factor. Okay, so let's talk about the amplitude factor and what you can consider for nodes if I talk. Okay, for nodes if I talk. For nodes if I talk, then this sin kx, this quantity should be equal to what? 2a into sin of kx should be equal to 0. So we know that this is the product of two things, 2a into sin kx. So this quantity can never be equal to 0. 2 can never be equal to 0. So what should be equal to 0? The sin kx should be equal to 0. Sin of kx should be equal to 0. So for which value of x, for which value of this kx, sin theta is what? 0. If you draw the graph of sine, so it will be coming like this. This is sin x graph. You can see that at this point, at the point here and this, at which you can see that the vertical displacement is what? 0. These are the points. What? At sin 0 we get the value of sin theta is equal to 0. At sin pi we get the value of sin theta is equal to 0, and 2 pi, like this the value goes on. Okay, that means for integral multiple of pi we get the value of sin theta to be 0. So this will be 0 when we can write like this the entire expression. That means sin of kx can also be equal to sin of n into pi, where n is the integer. Okay, for every n starting from 0, 1, 2 and so on, like this. We increase the value of n from 0, sin 0 will also be equal to 0. If we put n is equals to 1, then it will be getting sin pi, that is also equal to 0. So for every integral multiple of n, we will be getting the value 0. So if we compare this and this, if we compare that theta value which is there, so what we can get? We can get kx is equals to n into pi. Okay. So from here what we can get? We can get the value of x, the position of node, n pi upon k. That means in terms of this propagation constant and in terms of this integer, we can decide that at which point there will be the position of nodes in the entire string. Okay, so for n is equals x is equals to 0, if I put n is equals to 0, the value we will be getting x is equal to 0. That means in the starting at which the string is joined to the wall, from where the disturbance is created, there will be what? There will be the node where the amplitude will be 0. Okay, so what will be the second position for the node? If we put n is equals to 1, that means for pi upon k value. Okay, we will be getting the position of node. Similarly, here what we can do? Here we can place the value of this k. Here we can place the value of this k, that is propagation constant. And I told that k is also written as 2 pi upon lambda. Okay. So what will the value which we will be getting in more simplified form for the value of the position of node? N pi 2 pi upon lambda. So here n into lambda upon 2. So you can get the relation in between the wavelength and the position of nodes also. Okay, so you can see that here the wavelength of the standing wave we are getting. Okay, for n is equals to 0, for n is equals to 0, the value of x will be 0. That means in the initial there will be one node, and for n is equals to 1, the value of x will be coming how much? Lambda upon 2. Okay, that means in between the wavelength, in between the mid of that wavelength of the standing wave, one node we will get. Okay, so these are the position of what node. Let's talk about the position of antinodes, where the amplitude are maximum. Okay, where the amplitude is maximum. For antinode, this value should be maximum, and this maximum value of this will be what? Equal to what? This should be equal to 1. Okay, this should be equal to 1. That means we have to write that for every half integral multiple of sine, the value of this sine into a sine of what? We can write like this. The value of this sine kx will be maximum for every half integral multiple of what? Pi. Okay, for every sine of half integral multiple of pi, the value of this sine theta will be maximum. That means we can write like this also, if we neglect this 2a. Okay, so from here if we compare, kx is equals to m plus half into pi. Okay, so again put the value of k, that is 2 pi upon lambda. X into x is equals to m plus half into pi. Okay, so now what you can simplify it further. Pi and pi will cancel out and you can get the value of x, that is the position of antinode, and x will be equal to n plus half of lambda upon 2. This value will be getting. Okay, or if we simplify it further, then we get like this: 2n plus half lambda upon 4. Okay, so like this you can define that what is the position of the antinode in this case. Okay, so this is the expression that we got. Okay, so sometime in the question it may be asked that determine the position of nodes and antinodes. So but just by putting the same value here also, the value will be varying from n is equals to 0, 1, 2, 3 and so on like this. Okay, we can see that what will be the position of antinode in this case. So if we put n is equals to 0 in this case, what we will be getting? We will be getting the value lambda upon 4. Okay, so that means at a distance of lambda upon 4 from the origin, from this point of disturbance, we will be getting one antinode. Okay, and again for the value of n is equals to 1, we will be getting 3 lambda upon 4. Okay, so that means we will be getting another position at 3 upon 4 into lambda for the position of the antinodes. Okay, so similarly, if we are talking about the position of the nodes and antinodes, similarly we can talk about that what is the frequency variation in the entire string. Okay, and that is known as the normal modes. Okay, we can talk about the normal modes of the oscillating string. Okay, which is having the standing wave in it. Okay, so this is the required expression for the position of nodes and antinodes. So now let's talk about the frequency which will be created during the disturbance. So we have seen one condition in which we have seen that at x is equals to 0 there will be one node. Okay, so that means now let's talk for the value of n and onward. For n is equals to 1, 2 and 3 and onwards. Okay, so now we have to just neglect that n is equals to 0 which is written here. Okay, because n is equals to 0 is already satisfied for us. So for x is equals to, for the position of nodes if I talk, for x is equals to 0, we have seen the condition that at x is equals to 0 there is one node. Okay, so x is equals to n lambda upon 2. This is the equation that we have from there. Okay, so now let's talk about the boundary condition. Okay, we have talked about one boundary for x is equals to 0. Now let's talk about another. We have talked about this x is equals to 0 in this string. So now let's talk about the x is equals to L length. That means the other extreme of that string. Okay, the other extreme end of that string. So for that we will be talking for the remaining value of the n, that will be equal to 1, 2, 3 and so on like this. Because we have already talked about for the condition when n will be equal to 0. Okay, for n is equals to 0 we will be getting x is equals to 0, one position of the node here. So now neglecting that condition, we talk about some more condition which can occur. So from here you can put these value of the n. Okay, so at the boundary, at the other end of that string, the value of this x has the maximum limit of what? Has the maximum limit of capital L, that is the length of the string. Okay, because the length of the string is only the boundary, the other end is only the boundary. Okay, so at this point what I can say for the boundary condition, we can write that for x is equals to L, that means for the position of x is equals to L, there is what? This equation that we have from there. Okay, but the value of the n will be, now in this case will be from 1, 2 and 3 like that. Okay, because we have neglected the n is equal to 0 condition that we have already seen. If I would be writing here n is equals to 0, then we would be writing here the value 0. Okay, we would be writing here the value of what? 0. That means x was 0 in that case. But now we are just neglecting that term and we are talking about the other extreme of that wire, that stretched wire which is there. So here we can write that lambda is equals to 2 into L upon n. Okay. So this is the wavelength. This is the wavelength parameter which will be generated for the standing wave inside the stress string. Okay. But now can we relate this with the frequency term? Since we know that frequency is equals to the speed of light or the speed of the sound upon the wavelength. This we know. This is the frequency. This is the speed upon wavelength. We have the relation of this. Okay. So from here we can write that lambda can also be written as speed upon frequency. Okay. From this relation we can write. So 2 into L upon n. So from here, if we would know what to talk about the frequency, then what is the frequency formula we are getting? What is the frequency formula that we are getting? That will determine the normal modes. Okay. So frequency formula we have n into V upon 2L like this. Okay. Where n is varying from 1, 2, 3 and so on. Okay. So for value of the frequency, according to this value of frequency, by putting n is equals to 1 sometime, for the value of this frequency by putting n is equals to 2, n is equals to 3, n is equals to 4 and so on, we will be getting the certain modes of the oscillation. Okay, we will be getting some modes of the oscillation and that is said to be the normal modes in case of the oscillation. Okay, so when we put n is equals to 1, we will be getting the expression of V upon 2L for n is equals to 1. Okay, similarly for this is the frequency of the first mode, that is known as the first mode of the frequency, or one can say that this is also known as the fundamental modes of the oscillation. Okay, this is known as the fundamental mode. Or one can say this is the first harmonic. Okay, this is the first harmonic in case of putting n is equals to 1. And if we put the value n is equals to 2, then we will be getting V upon L. We will be getting V upon L. This is the value for n is equals to 2. This is known as the second harmonic. Okay, this is known as the second harmonic. Second harmonic. Okay, so if we draw the, similarly you get the third harmonic for n is equals to 3, similarly you get the fourth harmonic for n is equals to 4. Okay, by putting different value of the n, we will be getting different modes of the frequency, and that will be known as the normal modes in case of the oscillation of the string when the standing wave will be generated. Okay, so let us picturize these modes and let us see that how the fundamental modes, how the second harmonic or how the third harmonic looks like, okay, in the oscillation of the string when the standing waves are generated. So from this figure, from these figure you can see that how we can display the first harmonic, second harmonic, third harmonic, fourth harmonic and so on, which will be generated in the string during the production of standing waves. Okay, so here you can see the normal modes of the oscillation which are represented here. Okay, here is the expression for the first harmonic in which the frequency is how much? V upon 12. In this case, what will be the position of the, how many nodes will be there and how many antinodes will be there? Okay, according to the position that we have seen. Okay, according to that we can calculate that in this case, according to the expression of the position that we got in the previous time. Okay, so for this you can conclude that it will be having two nodes in case of first harmonic and two antinodes. Okay, here is the position of the antinodes. Okay, here is the position of the antinode which I denoted by A, and here is the position of the node. Similarly, you can talk for the second harmonic also. You can see that here there are nodes which are represented like this, where the amplitude is maximum. You just place the values of n in the position term that we got, okay, previously, and you can calculate that how much the value of what, how many nodes are coming and how many antinodes are coming. Similarly, you can see that one node is at this point, one node is at this point, and another node will be at this point. Okay, so for different values of n, substitute and get the values of node and antinode. Similarly, for here, for this also we can represent that there will be total 4 nodes in this case. Okay, for third harmonic. So this first harmonic is also known as fundamental mode. Okay, or fundamental mode. This is what represented by new one, that is the first mode of the oscillation. Okay, so here is another node like this. Here will be another node. Similarly, for this also, for fourth harmonic also, you can draw the position of nodes and antinodes. Okay, you can see. For example, if we talk about the first harmonic, then in that case we have to put. So let's see one question. This equation is the equation of string. Okay, in which this is the equation of a wave which is traveling in a string. Okay, in a stretched string. So in this we have to find that what is the wavelength that will be produced for that wave which is traveling. Okay, so this wave is very much similar to this expression. Okay, earlier we were writing something like this in terms of sine. Okay, we were writing like this, sine omega t minus kx, like this. Okay, for the wave traveling along the positive x direction. But sometimes we can write like this also. We can write this kx also before than this omega t. Okay, so here you can see that this type of the format is written. Okay, we were writing somewhere like this, that kx minus omega t in the bracket. So this expression is also true for the wave which is traveling, and that expression is also true. But in this case, what we have to do, this sine wave, this sine function can also be represented in terms of this cos function for a wave traveling, because this is also a sinusoidal function. Okay, so here if you compare this equation with this equation, that is, this equation is the displacement equation for the wave which is traveling. Okay, so in this we have to find that what is the wavelength. Okay, what is the wavelength, lambda, of the wave which is traveling. Okay, so if we compare this, then what we get? If we compare this, then we can modify this equation. 2 cos of 100 pi into t minus 2 of pi into x. Okay, in CGS we have to find. In CGS. So this, in this place of k, you can see that it is the equation, it is the quantity which is 2 pi. If we compare this and this equation, if it would have been written in sine, then we would be comparing this equation with this equation. But since this equation and this equation has not much difference in between, okay, so I am just comparing the formats which is given, which we know, okay, according to the given equation. So k, in place of k, it is 2 pi, you can see, and we know that k is equals to 2 pi upon lambda and is equals to 2 pi. So 2 pi will cancel out, and from here you can see that the lambda becomes equal to 1 centimeter. Okay, so this is the required value for lambda. So let this much be for today for this lecture, and this question is important. Okay, so thank you.